Hello, my name is David Stanier, and today I'll be talking about the magnetic tailoring and actuation of elastomer materials for large strain applications. So essentially what I'm doing is taking the skills we've learned from conventional carbon fiber composites, for example, in terms of their configurations and orientations, and applying this to large strain applications with elastomers. So just an introduction. Essentially what I'm doing is adding reinforcement to improve the properties of my rubber, but then I'm orientating this reinforcement so I can tailor the properties to the exact requirements that I want. But because I'm using this or intending to use this for large deformations, I need to use discontinuous fibers. And the use of these discontinuous fibers means that there's a possibility that we're going to get some reasonably significant differences between the conventional models that we'll use. But I'll discuss that later. But in essence, we observe two distinct stiffening effects. The longitudinal stiffening effect when the fibers are orientated parallel to the loading direction, and a transverse stiffening effect, which you can see on the diagram on the side, when the fibers are orientated perpendicular to the loading direction. So you can think of this like a Poisson effect. So the context for the research, what I've been working on for quite a long time now is finding a simple model that will validate our experimental data. And so essentially I started with a full 3D complex continuum mechanics model with multiple platelets with fairly variable orientation. And I simplified this down to a 2D plane strain model, and then I simplified this down again to a single platelet plane strain model. And what I've shown all the way along here is essentially how well these models describe the behavior and to what extent I can use the simplified model. And then I've taken the single platelet plane strain model and taken that and compared it to transversely isotropic constitutive models, which are normally used for continuous fibers. And what I'm seeing is essentially up to about 60% strain, which is reasonably considerable. I can get a fairly good match with my simple constitutive model. And I'll be using these models to help me tailor the materials to our requirements, and then also investigating the effects this orientation has on other properties, particularly magnetic, but it will also be permeability or the electrical properties. So what I've done is taken magnetic fibers. I've used nickel-coated carbon fibers. They're about 1/4 millimeter long, and we control the orientation by putting them in a linear magnetic field. After the material is cured, we've got orientated fibers which control the mechanical properties, but also because the fibers are paramagnetic, it means that we can actuate the fibers in a magnetic field. So the result is we've got reinforcing fibers that tailor both the mechanical and the magnetic responses of the material, and they do this in a complementary manner. So the applications. And obviously, as we all know, elastomers are extensively used in industry. They can be used car tires, dampers, or even gas masks in terms of their permeability. But for such a process, it can perhaps be argued this is difficult and expensive to implement at such a large scale. So what I'd be suggesting a potential application for this would be micro swimmers and micro actuators. So essentially what we've got is tiny little dynamic actuated swimmers which dynamically move in a viscous liquid. We can remotely actuate them because they're magnetic. And essentially at first we were using nanoparticles, and what we think is we've got the potential to use all the information we've used to reduce the size of this component. So we're thinking of high-performance applications in essence. So here you see the actuation, and what we can do is control the type of actuation by controlling the orientation of our fibers. So if they're orientated at 0 degrees, so the fibers are orientated along the y direction, we get a pure bending. And then if we introduce so in this it's through the page, so through the thickness, if we introduce some direction in this, we can get some twisting. So as you can see, that's at 60 degrees. If we use a 90-degree specimen, then we get pure twisting. So to conclude, we are using magnetic fibers pre-cure to control the direction of the reinforcement, and then post-cure, we're controlling the mechanical properties and the actuating direction, and this is a complementary effect. The response of the actuation is quick enough so that we can use it to envision a micro actuator or a micro swimmer. I'm doing this work at the moment, and we can use various configurations of the orientation. We can do through thickness orientation, or we can vary the orientation along the length of the specimen. It just depends on the magnetic field lines. So thank you very much, and I would invite any questions.